Good morning, and thank you guys for joining today's webinar. Today's topic is how to get the best performance out of your Seismic web applications. A few housekeeping things. If you notice in your interface, there's a Q&A section. If you want to add your questions there, we can get to them as soon as it makes sense, either within the, during the presentation or at the end. Or if you'd like to raise your hand to ask the questions in real time, we can also ask. Today's presenters will be Mikhail Gushinets and Serge Peregrine. They're both developers here at INT, and they can tell a little bit more about themselves as they go. Again, thank you for joining, and the session will be available after the webinar is finished. Give me about 2 days, and I'll get it out to you via email. Okay. All right, Mikhail, take it away.
Okay. Thank you, everybody, for joining us. And today we'll be speaking about different ways of increasing performance of your seismic data. And we will dive deeper into details of modern technologies like SIMD and WASM that can be useful to achieve this kind of speed up. Okay, what is IVAAP? Just to introduce, IVAAP is our flagship product, and this is our data visualization platform. It consists of 3 main parts. IVAAP client that provides 2D and 3D widgets, sessions, and templates. IVAAP server that connects to multiple data sources and provides workflows. And also the third part is IVAAP admin. It manages user access and projects. Let's take a closer look at IVAAP architecture. As I said, this is server and client architecture, and they interact like this. So client requests file to display from server. Server returns file list. User chooses particular file to display, and then server starts sending chunks of data, and client displays this data. What issues do we have in this scheme? First of all, our main issue is that seismic data files can have huge size. They can be hundreds of gigabytes and even several terabytes. So this is why it takes too much time to transfer via network. And also network can have different bandwidth. So our goals are to speed up file transfer time, reduce data size for transfer, and add some kind of user controls for different network bandwidth. What was the solution that we applied? We decided to implement server-side compression and client-side decompression. And also we decided to provide the client parameter that we called acceptable error level after seismic data compression and decompression process. Let's take a closer look at compression and decompression process. So original seismic data goes through a set of 5 transformations: AGC, normalization, higher wavelets, quantization, and last Huffman. As a result of this transformation, we get a compressed file that we can send to client via network. And on client side, there is a decompression process that goes in different direction, from inverse Huffman to inverse AGC. And this is the way that client gets original data. As you can see, it gets not precisely original data, but it gets data after compression and decompression process. So that's why we decided to add this acceptable error level after compression and decompression process, because we have different scenarios when client doesn't always require the full original data with full level of precision. For example, sometimes client needs only preview of seismic data. So using this acceptable error level, he can control how much data will be passed via network, and of course to speed up this process. So the resulting scheme looks like this. Client requests a file list from server, user chooses particular file to display, and then server starts sending chunks of data. It compresses this chunk, sends to client decompresses and displays this chunk. And this procedure is repeated for each tile to display. You may be wondering why not use any other existing compression, for example, gzip, which is already implemented and supported by most modern browsers. We tried this compression, but we found out that this type of compression is not as effective on our particular seismic data as we want to. Moreover, as I said, we need this kind of lossy compression and to provide controllable error level on client side, which obviously cannot be implemented with lossless compression algorithms. So our task was to speed up current implementation of compression and decompression procedure both on server and client side. Server-side compression is implemented in Java. So we decided to create C++ implementation of compression sequence and use Java native interface layer to call native methods. Same for client side. We decided to implement, because client side decompression is implemented in JavaScript, we decided to create C++ implementation of decompression and use WebAssembly proposal for integrating C++ code into JavaScript. We implemented both compression and decompression algorithms in C++, but after comparing the results of performance of C++ and Java code, this was a point of disappointment for us, because we found out that C++ code was just 1.5 times faster than warmed up Java code. That's why we decided to move on and to apply SIMD instructions for further speed up. Let's take a closer look at SIMD instructions. SIMD stands from single instruction, multiple data. So what is SIMD? As you can see on the left picture, in order to apply addition of A and B and get the results of C0, C1, C2, and C3, we have to execute 4 operations. SIMD allows applying one instruction over vector of values, not over scalar values like on left picture, but over vector of values. The results of this approach are pretty good because SIMD, what are SIMD benefits and SIMD drawbacks? SIMD approach allows processing several data values with one single instruction. That's why we can achieve much faster computation on predefined computation patterns. And what are drawbacks of SIMD instructions? SIMD operations cannot be used to process multiple data in different ways, like on this picture on the right side. So we cannot apply SIMD instructions to process values when we first apply addition, then subtraction, then, for example, multiplication or division or something else. So we can only apply SIMD operations to predefined processing patterns with independent data handling. So when data on current step do not depend on calculation of data from next step or previous step. SIMD instructions firstly were introduced in 1997 by Intel, and when they presented MMX technology. MMX stands for multimedia extensions, and this was the first vector extensions that was available. After that, they also introduced new extensions like SSE, the whole family of SSE, SSE 1, 2, 3, and so on. Then AVX family, AVX 1 and AVX 2, and also AVX 520. What is the main difference between these instruction set? The main difference, as you see, is the size of processor registries that can contain data for further calculations. For example, MMX extensions only support 64-bit registers. SIMD SSE instructions extend the size of registries to 128 bits, and so on with AVX and AVX 520. Let's take a closer look at a real example. On the left side, you can see normalization. You can see implementation of normalization algorithm. It looks pretty simple. For each value from input data array, we divide this value by maximum amplitude and write the result of this division into output data. As simple as that. On the right side, you see how this algorithm is implemented, well, can be implemented using SIMD SSE instructions. First of all, in order to use SIMD intrinsics, you have to include imm_intrin.h header file. Then you can see this data type M128. This data type can this data type has 128 bits. Its capacity is 128 bits, and so it can contain, for example, 4 floats, each one 32 bits, or it can contain 2 doubles, each 64 bits, or it can contain 4 integers, as you like. In this line of code, we load, we fill the vector multiplier with 4 values. Each one is equal to max amplitude. Then we use this while cycle to handle 4 values from input array at one time. So we load next four floats from input array P in, and by this single instruction, we multiply work vector by multiplier vector, and we get the result of this multiplication into result vector. And using this instruction, we store or unload these values of result vector to pointer of P out. Then we move pointers to 4 values ahead and decrease number of already handled floats. So this is it. As you can see, we in scalar implementation, we use one operation for each value from input data, and with SIMD instructions, we use only one operation that handles 4 values at almost the same time. This is the speed up. What kind of speed up did we achieve on server side? As you can see, we achieved different speed up levels for different algorithms. For example, normalization was 9 times faster than scalar C++ version. Hard wavelets SIMD implementation was 6 times faster than scalar C++ version. And Huffman didn't get no performance increase because this algorithm is not vectorizable, because it doesn't have any predefined pattern for calculations. So overall server-side compression performance improvement was about 3 times faster than Java version. This is applying SIMD C++ code, which was pretty good for us, and we decided to move on to client-side speedup. And my colleague Serge will tell you more about this work.
Thank you. So the client parts of application is written in JavaScript, and the Seismic decompression was implemented in JavaScript as well. And to improve this application, we decided to use WebAssembly for it. So some words about what WebAssembly is. WebAssembly is an open standard that defines first binary format, which is portable and can be executed in stack-based virtual machine. It defines the corresponding textual assembly language. And finally, it defines the interfaces for interaction between WebAssembly program and the host environment. And high-level language can be compiled in WebAssembly, at least C and C++ can. Also, the main purpose of WebAssembly was to enable high-performance application for web pages. It can be integrated and executed in other environments, or even used as standalone applications. As far as we have the C++ implementation of decompression, we use it. To create the WebAssembly models, we use mscripten. Mscripten is a complete compiler toolchain to WebAssembly. It's based on LLVM project. This toolchain creates the WebAssembly model, which can be embedded into HTML document or loaded as node model. But often some kind of JavaScript glue code is needed to embed this model into JavaScript application. This glue code may consist of some initialization, checking, data conversion function. And also it contains binding function. Binding function needed to be able to call the C++ functions and use C++ classes into JavaScript. In this slide, we can see an example of C++ code, part of this glue code. This code is binding function of C++ to some JavaScript names. In the left part, there is a C++ class definition. It consists of a constructor with some parameters, couple of setters, and a process function which make the filter works. In the right part, there are some calls to inscript and bind the C++ class and its function with some names. These names can be used in JavaScript as JavaScript class name and JavaScript function. JavaScript with class functions. The names of JavaScript part are in quotes. Also, there are possibility to bind getter and setters from Java or from C++ class to the JavaScript, and also possible to bind C++ class fields. It's not shown here, but it's possible. JavaScript part of glue code can contain some checking initialization data and also data conversion function. Data conversion functions are necessary because of not plain data representation for JavaScript and C++ are different. And in this slide shows the usage of this class and function in JavaScript. First of all, this type filter WASM is created. To create it, the name defined in the bind code is used. And then there is a function apply. This is a JavaScript function apply. And inside this function, the apply function from C++ class are called. But before we can call this function, we should convert data, input data from JavaScript representation. In this case, this is a float 64 array or some kind of typed array. We convert it to representation with which the C++ function can work. Actually, this is not simple conversion. It's copy data from JavaScript memory to WebAssembly memory. And after the function apply is returned, the back conversion needed. This function converts the standard template library vector data to float 64 array. And this is again copy data from WebAssembly memory into JavaScript memory. This function, this conversion function, can cause some performance degradation. And actually in this case, this function takes about a third part of the whole execution time. So the calls of this function should be minimized. And as for about our decompression implementation, we convert the data from JavaScript representation to the C++ representation and back only once before the full compression change, and after we convert it back. Also, there are an effort to use SIMD instruction in WebAssembly. And currently, the 128-bit SIMD instruction are supported by mscripten. So, to enhance the WebAssembly application, we enhance performance of this application, we try to use this instruction. We implemented a seismic decompression algorithm with SIMD instruction, and significant enhancement was received. So, as you can see, inverse normalization has 6 times speedup, and higher wavelet 10 times speedup. Inverse Huffman, no performance improvement, as this algorithm, it seems to be not vectorizable. And the overall decompression performance improvement with vectorized C++ code we get was about 6 times faster than JavaScript decompression code. But not all this was good, because there is a problem. This problem is that the currently WebAssembly SIMD extension has an experimental status, and it seems to be only Chrome browser with version not less than 84 supports it. And this support is turned off by default. So right now we cannot use this solution in production. But anyway, we are able to use the WebAssembly and get some performance improvement. Our WebAssembly seismic decompression implementation is about 2 times faster than JavaScript implementation. So that's all. Thank you.
Okay, guys, if you have any questions, you can write down your questions in question and answer section. In the meantime, I will show you the demonstration of our IVAAP client and server interaction. So this is a client, and we open project. It's loading. Here we can choose seismic data. So we have our data, seismic data loaded. As you can see, it is loaded by tiles. So which tiles are not visible, there is no reason to load them. You can see that I'm moving the slice and the tiles are loading. We can use no compression. So now we receive data, seismic data with no compression at all. And we can activate higher wavelets compression. So here it is already. And about this maximum error level that I spoke about, client can control the level of acceptable error level. So we can, for example, move it further. We can set it higher, or we can set it less. No difference for me in the visual representation. Okay, let's set it to maximum level of the maximum value of 15. Well, as you can see, now we have a visual degradation because we set this level pretty high. Let's set it back to 1% and set it back to 15. Yes, now it's obvious that we have, by increasing the maximum error level, we achieve better compression, we achieve speed up by the cost of losing some data and having some even visual degradation of seismic data. Okay, guys, do you have any more questions?
So, okay, so I do have one. What compression rate does the HAR wavelets compression that you apply? What's the compression rate there?
Yeah, about compression rate of HAR wavelets. Well, I can say that it really depends on several parameters. First of all, and mostly it depends on the distribution of seismic data itself. And for example, for most difficult files to compress, we have a compression ratio about 4 times. And this compression ratio is increased up to 13 times. So in general, this is all these values I'm telling you with maximum error level 1%. So when client requests almost the same seismic data as original. But if you want more compression ratio, you can increase maximum error level, and the compression ratio can raise up to 20 or even 30 times. But of course, by the cost of losing a lot of original data. So this is up to client.
Okay, and then we have 2 in the Q&A. Are you using VDS or something different here?
Right now, we're not using in this demonstration VDS, but we are implementing support with VDS, so it's coming. Okay,
and what is the size of the volume you can manage?
Actually, as I told about the scheme of interaction between server and client, we request seismic data by tiles. So as long as server can send these tiles, client can handle it.
So just want a point of clarification, VDS is already available, just not, you said not in this demonstration, right?
Yeah.
Okay. Perfect. All right, the session is recorded, so we'll have this available later if you want to review, or if you want to share with someone on your team.
Thank you. Thanks everybody who joined. Thank you for your attention and for your interest in this this theme